Hello everyone, welcome back. So another data analysis video, and I'm still on the topic of data wrangling and cleaning data, so it's in some sort of tidy order so you can conduct analyses. In the previous couple of videos to this, I kind of demonstrated how to normalize and standardize data and how to deal with outliers. In this video I'm going to cover data transformations. So there's quite a bit to cover here, so I'll probably split it across a few videos. In this video, I'll probably talk about imputing data, so how to deal with missing values in data and how doing so might affect the distribution of the data. And then in the following videos, what I'll do is I'll take some sort of variable from a data set that's kind of not normally distributed, and I'll demonstrate the different types of transformations you can perform on it to see if you can make it more normally distributed. Okay, so basically we use data transformations to deal with problems of normality and linearity in a data set. And the idea behind transforming data is that you do something to every score using some type of mathematical function in order to correct for issues with the data not being normally distributed, or a lack of linearity in the data, or unequal variances. So the variance isn't constant along the whole scale of the variable. So common issues often also involve things like the data being skewed, or issues of kurtosis, so it being very highly peaked or flat, that type of thing. And if you're using some type of statistical model or machine learning algorithm that assumes data is normally distributed, such as linear regression or logistic regression, then it might be necessary to transform your data, to transform a variable to make it more Gaussian, so it looks more normally shaped, so it fits kind of the assumption of a normal distribution. And another assumption of such models is that there's a linear relationship between the predictor and outcome variables. And if these are not met, then the parameter estimates that are returned by these types of general linear models, these parametric statistical models, will likely be incorrect, and the model will produce erroneous results. So as an example, linear regression, it makes the following assumptions about data used in a model if we were to fit some sort of linear regression model. And linear regression is using a straight line to model data, and it's the basis of a lot of statistical analyses, such as linear regression, multiple regression, logistic regression, even ANOVAs, where you're looking at categorical data. So there's some of the assumptions of regression are that there's a linear relationship between the predictor and the outcome variable. Multivariate normality is also an assumption, so all variables should be multivariate normal, and there's no direct test to this, so it's best checked by looking at histograms and QQ plots or probability plots. Multicollinearity, and that's the assumption that the predictors, the independent variables, are not too highly correlated with each other, and also homoscedasticity, or constant variance, so the assumption is that there's equal error variance across all values of the predictor independent variable. Okay, so I'm not actually going to run linear regression in this. I'm just going to demonstrate in this particular video. I'm just going to demonstrate some sort of data transformations, and I'll start with dealing with kind of large numbers of missing values and the influence that can have. So I'm going to import a number of libraries, software libraries, into Python. I'm going to use pandas, import that as PD, import numpy as NP, matplotlib.pyplot as PLT. I'm going to import seaborn as SNS in case you want to use it, and I'm going to import scipy.stats as stats, because I will probably use scipy at some point to demonstrate the data transformations that I'm going to use in the next couple of videos. So what I'm going to do is I'm going to import a data set, and it's the Titanic data set, which you can find this readily available online in different places. And it's I've got it saved as a CSV on my laptop, so I'm going to use the pandas read_CSV method and import that. I might have demonstrated some kind of analysis or data cleaning techniques with this data set before, but this is actually data from the Titanic that contains information about who survived, who died, the class with passengers, sex, age, various other things. Okay, so let's have a look at some of the info in this data frame. We've got a number of variables, 891 entries altogether. So age, fare, cabin, where they embarked from, sex of the passenger, the class, first, second, third class passenger, whether they survived or not, things like that. And I'm going to focus on a couple of variables. One of them's age, and it's got 714 non-null values, so it's missing quite a lot of data. There are a number of missing values in terms of age in this data set. So what I'm going to do is I'm just going to focus on two variables for these next couple of videos. I'm going to focus on age in this video and then probably fare in the next one. And I'll import also the survived data in save this as kind of a separate data frame, a smaller data frame. And if I call the head there, you can see all I've done is extract these three variables from the main Titanic data set. Maybe survived is it might be our outcome variable if we were doing some sort of logistic regression and we're trying to predict whether someone survived or not based on the fare they paid or based on their age. But anyway, what I'll do is for this new data frame, this small data frame object, let's have a look at how many null values we've got. And you can see there we've got 177 missing values for age. So that's quite a lot in a data set of 890. So, you know, we're talking about nearly a fifth of the data there is missing. So there are a number of ways we could deal with this. We could just drop those 177 rows with missing values, but that means dropping an awful large percentage of the data available to us, or we could try to impute data for those missing values so we don't have to throw away participants. So here what I'll do is I'll demonstrate how to fill those values using a specifically written function that does imputation. It'll create a couple of new variables for us based on age, one where it's imputed the missing values using just the median age value in our data set, and another where it fills those missing values with random values based on the ages in the data set. Okay, so to do that here, what I've done in this cell is define a function called impute underscore NA, so impute missing value, and it's going to create two new variables for us. As I said, one that's going to replace missing values with a random number based on a sample from the ages, and one that's going to fill it with the median value. So every missing value will get the same median value. And if you've not seen this before in Python, to define a function, you use this def argument, then you state the name of the function, and in parentheses you put the arguments that you have to pass, the parameters that the function takes. And all I'm doing here is defining basically two things. I'm going to say that our data frame we're going to create a new variable, which is whatever the variable name is we pass into the function, underscore median. And to do that, we're going to take whatever that variable is and just fill missing values, fill NA with the median score. So replace any NA value, not a number value, missing value, with the median for the data for that variable. Secondly, we're going to create a second variable which is going to have the variable name and random. In this case, we're going to use age. So this will create two new columns essentially in our data frame object called age median, age random. But this time what we're going to do is fill it, rather than filling it just the median, we're just going to fill it with a random sample. So to calculate the random sample, we're going to create this new object called random underscore sample, and then we're going to say drop NA from whatever the variable name is, and then sample. And if it's null, we're gonna basically replace it with a random value, and I've set like a random seed of 0 there. So we also want to match all the missing value indices in random sample with those for the data frame. So pandas needs to have the same index in order to merge this data set with the existing data set. So that's what this second this other line here says. It says random sample index. The variable name is null.index. And this final line here is just basically locate all the null values and replace them with random sample essentially. So let me run that. And what I will then do is I'll create a new object for the median, and all I'm doing here is taking our data frame, taking the age variable and calculating the median, and then I'm going to, here in this cell, I'm going to call this function we've defined. I'm going to pass the data frame, the variable we're interested in, which is age, and then and as the median, rather than stating it as a value, I'm going to pass this object which contains the value of the median for our data frame. So if I run that, what we get is this panda, this warning saying doesn't like it. It's it's telling us essentially we're taking a copy of a slice of a data frame. But if I run the head document, you can see it has actually worked. There's some issue it doesn't particularly like about it, but it has worked, and we've now got these two new variables. One where any missing value for age has been replaced by the median value for age, and one where any missing value for age has been replaced by a random sample of values essentially. Okay, so if we now look at how many null values we've got, you can see for the age variable, we've still got 177, but for our median and age median and age random, these two new variables that are based on age, there are now missing values. And if we look, we haven't lost any. There should be 891, and there are. So we now have a data point in these two variables that represents in place of what were these 100 and odd missing values, 177 missing values, I think, in the Titanic age variable. Okay, so that seems to have worked, and the two new age median age random variables have 891 null values. So they're the correct length. It seems to have, Panda seems to have merged it correctly, and all missing values have been replaced with some number, either the median or a random age. Okay, so what we'll do is we'll create a plot now, and all I'm doing here is using matplotlib. I'm creating a plot, and I'm using the dot plot function, which will just give us a line plot, and I'm asking for the kind that I want is a KDE, so it's going to give us kernel density estimators. So if I run that, what you can see here is, so the blue line is our original age variable with 177 missing values. The yellow line is the distribution of data where we've replaced missing values with the median, and that differs. It's changed it considerably, and it's sort of now the distribution of scores is different to the original variable. And the red line is where we imputed a random sample of values, and that quite closely matches the original data. Okay, so that's quite interesting, that using a random sample rather than median seems to have kind of preserved the kind of distribution of the data. And it appears here that using a sample of random values was probably a better approach. And what we can do is we can kind of use histograms and probability plots to investigate which of these variables is the most normally distributed. So what I'm going to do here is I'm going to examine the data using a histogram and a QQ plot. I'm going to put them side by side, and I'm defining a specific function. I'm calling it diagnostic plots, that presents both of these as subplots in the same figure, so they'll be next to each other. It'll give us the shape of the distribution as a histogram, and it'll then also give us the QQ plot, so we can see how normally distributed it is. So if you look here, I'm defining it using the def keyword again to define a function. I'm calling it diagnostic plots, and it's going to take a data frame name and a variable name, and then I'm creating plt.figure, so I'm just creating a new plot figure, and I'm telling matplotlib to use subplots. I want one row, I want two plots. The first plot, which is this third number one here, is going to be whatever the variable we put in. In this case, we're going to use age, and it's going to be a histogram. The second subplot is going to be a probability plot, and where we want it to be based on a kind of normal distribution. So if I run that, create that function, then what we'll do is we'll use diagnostic plots on the original age variable, and then this random, the new age random variable where we kind of imputed those missing values. And if I run that, what you can see here is you can see the distribution of the age variable looks slightly positively skewed. It's not particularly normally shaped, and we can see that it is deviating quite a bit. So if this was normal, then we should see like the line, the dots, the data points would sit along a line, in a straight line along this axis. So the predicted versus observed, essentially. So not normally distributed. So that could be an issue. But if we run the same thing on our changed variable, our transformed variable where we imputed, what we can see here is the shape, the distribution is kind of still the same shape essentially, but we're getting a much more normally distributed sample. And this seems to be, that by using a larger sample, we've kind of removed a bit of uncertainty in the data. So where we're losing, where we're kind of in this, where we've got 177 less data points, the extent to which it's we think it's normally distributed is much great. It deviates much more greatly than in this second plot. So it's still skewed. So if we look at the age random variable with the imputed values, we can see it's still slightly skewed, but it has a much more general Gaussian distribution when we look at the probability plot. The shape of it, I mean, it deviates away at the tails. That's often a common thing. But this, if we used the age random variable rather than age in some analysis, it's not going to be, it doesn't seem like it'd be too problematic in a parametric statistical test. It seems like we could assume that it's appropriate for a parametric statistical test that makes the assumption that data is normally distributed. Okay, so that is dealing with missing values that might influence the extent to which your data appears to deviate from normality. And you can see here by kind of imputing a random sample, it seems to have helped us to kind of it seems to have helped us to create this variable that is better suited for use in a parametric statistical model. Okay, so in the next video, what I'll do is I'll focus on a different variable and I'll demonstrate a number of different ways you can actually transform the shape of data. So in this video, I just looked at missing data and how that might affect some of the assumptions you have to meet, and how imputing data points, how doing so might help overcome that. In this case, what we found was that using a random sample to replace missing values seemed to produce a better result. Okay, hopefully that was useful.